In Dijkstra's algorithm, we find shortest distance from source vertex to all other vertices in the graph. It gives correct results only if all the edge weights are non-negative. For example, in this graph, if we take 0 as the source vertex, then using Dijkstra's algorithm, we can find shortest path and shortest distance from vertex 0 to all other vertices of the graph. Now let's see how Dijkstra's algorithm works. We'll give each vertex a status. This status can be temporary or permanent. If the status of a vertex is temporary, it means the shortest path to it has not been finalized. And if the vertex is permanent, it means that the shortest path to it has been finalized. Now, initially all vertices have temporary status, and in each step of the algorithm, we'll change the status of a vertex from temporary to permanent. That is, in each step, we'll finalize the shortest path to a vertex of the graph. Each vertex will be labeled with path length and predecessor. At any point of the algorithm, path length of a temporary vertex denotes the length of shortest path from source vertex to any vertex v known till now, means known till that point of the algorithm. As the algorithm proceeds, we might get a better path from source vertex to vertex v, and in that case we'll change the value of this path length. Now, predecessor of a temporary vertex denotes the predecessor of v in the shortest path known till now. For a permanent vertex, this path length denotes the length of shortest path from source vertex to v, and predecessor denotes the predecessor of v in the shortest path. Now, when the algorithm starts, the path length of all vertices is initialized to infinity, which denotes a very large number. And predecessor of all vertices is initialized to nil. This nil can be any number that does not denote a vertex. Our vertex numbers start from 0, so we will take this nil to be -1. During the algorithm, the path length and predecessor of a temporary vertex can be changed many times. Whenever we'll get a shorter path, we'll update these values. When we change these values for a vertex, we'll say that we are relabeling that vertex. So a temporary vertex can be relabeled, but once a vertex is made permanent, it will not be relabeled because shortest path to it has been finalized. We have seen that initially all vertices will be temporary, and in each step of the algorithm we'll make a temporary vertex permanent. Now, to choose the vertex that is to be made permanent, we'll use the greedy approach. In greedy approach, we generally perform an action that appears best at the moment. So in this algorithm, we'll take the temporary vertex with minimum path length and make it permanent. Now let's see the whole stepwise procedure of the algorithm. Initially, for all vertices, path length is equal to infinity, predecessor is nil, and status is temporary. Now first we make the path length of source vertex equal to 0. Now from all the temporary vertices of the graph, we'll find the temporary vertex which is minimum path length and we'll make it permanent, and it becomes the current vertex. At the start of the algorithm, source vertex has minimum path length. So the source vertex will be the first one to become permanent. In the second step, we'll examine all temporary vertices adjacent to the current vertex and we'll relabel them if required. Now let's see what's the condition when we need to relabel any temporary vertex adjacent to current vertex. Suppose V is a temporary vertex adjacent to current vertex that we are examining. Now if path length of current vertex plus weight on this edge is less than path length of vertex V, then we'll relabel the vertex V. Now path length of V becomes equal to path length of current plus weight on this edge, and now current becomes the new predecessor of vertex V. If this value is greater than path length of V, then no relabeling is required. Now these steps 1 and 2 are repeated till either there are no temporary vertices left in the graph or all the temporary vertices that are left have path length equal to infinity. At the end of the algorithm, the temporary vertices that are left with path length infinity are those vertices that are not reachable from the source vertex. Now let's understand with the help of a figure how this relabeling of a temporary vertex is done in this step 2. Suppose S is the source vertex and C is the vertex which we have recently made permanent. So it is the current vertex. These are the labels. Labels of permanent vertices are fixed. They are never changed. Now this 6 is the value of the path length. So it is actually the length of the shortest path from source to this vertex. This vertex C is permanent. It means that this shortest path to C is final. Now predecessor of this vertex C in this shortest path is vertex P. Now we have to examine the temporary vertices that are adjacent to this current vertex. Suppose we have these 3 temporary vertices adjacent to this vertex C and these are the labels. Now these are temporary vertices, so their labels are not fixed. We can change them whenever we get a shorter path. First let's examine this vertex V1. Path length for it is 10. It means that till now the shortest path that we know from S to V1 is of length 10. And the predecessor of V1 on this path is vertex X. Now we check this condition for this vertex V1. Path length of current vertex is 6. Path length of V1 is 10. And the weight on this edge is 2. Now 6 plus 2 is less than 10. So this condition is true. It means that we have found a shorter path to vertex V1. Till now we knew that shortest path to V1 was of length 10. Now we have a path of length 8, which is made up of 2 parts. A path from S to C and an edge from C to V1. So we relabel this vertex V1. Now value of path length is 8 and C is the predecessor of vertex V1 in the shortest path. Now let's examine this vertex V3. Path length of V3 is 8. It means that till now the shortest path that we know from S to V3 is of length 8. And the predecessor of V3 on this path is vertex Y. Now let's check this condition. Path length of this current vertex is 6. Path length of this vertex V3 is 8. And the weight on this edge is 3. Now 6 plus 3 is greater than 8. So this condition is not true. So there is no relabeling required for this vertex V3. It means that using this vertex C, we did not get a better path to vertex V3. This path was of length 8 and this path that we get using this vertex C was of length 9. So we did not change the label of this vertex V3. Now let's see this vertex V2. Now for this vertex V2, path length is infinity and predecessor is nil. It means that we have not found any path till now from S to vertex V2. So definitely this condition will be true. 6 plus 5 is less than infinity. So we'll relabel this vertex V2. Now in the next video, we'll take a graph and understand the whole procedure. In this video, we'll understand the procedure of Dijkstra's algorithm with the help of this graph. Now, initially, all vertices are temporary. Path length of all vertices is infinity and predecessor for all vertices is nil. Now, we'll take vertex 0 as the source vertex. So, at the end of the algorithm, we'll be able to find shortest paths from this vertex 0 to all other vertices of the graph. Now the first step is to make path length of source vertex 0. So we make path length of this vertex 0 equal to 0. Now from all the temporary vertices, we have to find the vertex which has minimum path length. So this vertex 0 is a vertex with the minimum path length. So we'll make it permanent. Now this vertex 0 is our current vertex. Now we have to examine all the temporary vertices that are adjacent to this vertex 0. So these are the temporary vertices 1, 3 and 4 which are adjacent to this vertex 0. So now we'll examine these vertices one by one. Now first we'll examine this vertex 1. Path length of this vertex 0 plus weight on this edge is less than path length of vertex 1. So we'll relabel this vertex 1. Now 5 is the path length of vertex 1 and 0 is its predecessor. Next we take this vertex 3. Path length of vertex 0 plus weight on this edge is less than path length of vertex 3. So we'll relabel this vertex. Now 2 is the path length of this vertex 3 and 0 is its predecessor. Similarly, we'll take this vertex 4 and it will be relabeled. Now from all the temporary vertices, we have to choose the vertex that has minimum path length. This vertex 3 is the vertex with the minimum path length. So we'll make vertex 3 permanent. Now this vertex 3 is our current vertex. We have to examine all the temporary vertices that are adjacent to vertex 3. Vertices adjacent to vertex 3 are 4 and 6 and both of them are temporary. So we'll examine vertices 4 and 6. First we take this vertex 4. Now path length of 3 plus weight on this edge is greater than path length of 4. So there is no need to relabel this vertex 4 because we already have a path from 0 to 4 which is of length 8 and using this 3 we get a path of length 9. So there is no need to relabel this vertex 4. Next we take this vertex 6. Path length of 3 plus weight on this edge is less than path length of 6. So it will be relabeled. Now from all the temporary vertices, this vertex 1 has a minimum path length. So we'll make it permanent. Now this vertex 1 is our current vertex. We have to examine all the vertices that are adjacent to vertex 1 and are temporary. There is only one vertex adjacent to vertex 1 and it is temporary. So we'll examine this vertex 4. Now path length of 1 plus weight on this edge is less than path length of 4. It means that we have got a shorter path. Till now the path from 0 to 4 was of length 8. But using this vertex 1 we have got a path of length 7. So we'll relabel this vertex 4. Now path length of this vertex 4 is 7 and predecessor is vertex 1. Now from all the temporary vertices, this vertex 4 has a minimum path length. So we'll make this vertex 4 permanent. And now this vertex 4 is a current vertex. Vertices 5 and 7 are adjacent to this vertex 4 and both of them are temporary. So we'll examine these vertices 5 and 7. Now both of them have path length infinity. So definitely both of them will be relabeled. Now from all the temporary vertices, this vertex 6 has a minimum path length. So now we'll make vertex 6 permanent and now 6 is our current vertex. There is only one vertex adjacent to this vertex 6 and it is temporary. So we'll examine this vertex 7. Now path length of vertex 6 plus weight on this edge is greater than path length of 7. So there is no need to relabel this vertex 7. Now from all the temporary vertices, this vertex 7 has a minimum path length. So now we'll make vertex 7 permanent and now this vertex 7 is our current vertex. Now vertices adjacent to this vertex 7 are 5 and 8 and both of them are temporary. So we'll examine these vertices 5 and 8. First we take this vertex 5. Now path length of vertex 7 plus weight on this edge is less than path length of vertex 5. This means that we have got a shorter path. Till now, the shortest path that we knew from vertex 0 to vertex 5 was this. It was of length 16. Now using this vertex 7, we got this path which is of length 14. So we'll relabel this vertex 5. Now its path length is 14 and its predecessor is 7. Now we come to this vertex 8. It is path length infinity, so it will definitely be relabeled. Now from all the temporary vertices left, this vertex 5 has the minimum path length. So we'll make vertex 5 permanent. Now this vertex 5 is our current vertex. Now we have only one vertex that is adjacent to this vertex 5 and it is not temporary. So next we'll make vertex 8 permanent because from these two temporary vertices left, this vertex 8 has a minimum path length. So now our current vertex is vertex 8. We have only one vertex that is adjacent to this vertex 8 and this vertex is permanent. So there are no temporary adjacent vertices. Now we have only one temporary vertex left and it is path length infinity. In the previous lecture, we had learned that the algorithm stops when either there are no temporary vertices left or all the temporary vertices that are left have path length infinity. Now we are left with one temporary vertex and it is path length infinity. So it is time to stop our algorithm. We had also learned that all the vertices that will be left with path length infinity will be those vertices that are not reachable from the source vertex. So here this vertex 2 is the only vertex that is not reachable from the source vertex 0. Now at the end of the algorithm, the path length and predecessor of all the vertices have been set. Now we can easily find shortest path from vertex 0 to any other vertex by following the predecessors till we reach the source vertex. Suppose we have to find shortest path from vertex 0 to vertex 6. Now predecessor of vertex 6 is 3 and predecessor of vertex 3 is 0. So this is the shortest path from vertex 0 to vertex 6. Now suppose we have to find shortest path to vertex 8. Now predecessor of vertex 8 is vertex 7. Predecessor of vertex 7 is vertex 4. Predecessor of vertex 4 is vertex 1 and predecessor of vertex 1 is vertex 0. So this is the shortest path from vertex 0 to vertex 8. In this video, we'll see the implementation of Dijkstra's algorithm. In this class vertex, we have taken these three additional members: status, which can be temporary or permanent, predecessor, and path length. Now in this class directed graph, we have taken these four constants. These two constants are for specifying the status of vertices. This constant nil is used to initialize the predecessors and this constant infinity is used to initialize the path length of all vertices. Now in this method Dijkstra, we'll apply the Dijkstra's algorithm to set the predecessor and path length values of all the vertices. We'll call this method in the public method find paths. This is the public method find paths. We are calling Dijkstra's algorithm here. So first let's see how this method Dijkstra works. Now at the start of the Dijkstra's algorithm, all vertices are temporary and path length of each vertex is infinity and predecessor of each vertex is nil. First we make the path length of source vertex equal to 0. The index of the source vertex S is sent as argument to this method. Now in this loop, first we find the temporary vertex with minimum path length using this method. Now let's see this method. This method will return the temporary vertex with minimum path length and it will return nil if there is no temporary vertex left or all the temporary vertices that are left have path length infinity. Now the vertex returned by this method becomes the current vertex. If nil is returned by this method, it means that either there is no temporary vertex left or all temporary vertices left have path length infinity. So in that case, our algorithm finishes and so we'll just return. Now if nil is not returned, then we come here and we make vertex C permanent. Now vertex C is our current vertex. Now in this loop, we check all the vertices that are adjacent to vertex C and are temporary. and we relabel all those vertices which satisfy this condition. Now this while loop is an infinite loop, so this process will stop when this method returns nil. In that case, we'll just return from this Dijkstra's method. Now we have called this method Dijkstra in the public method find paths. So now let's see the public method find paths. In this method, the name of the source vertex is sent as argument. There we find the index of source vertex. Then we call this method with index of the source vertex. After this call, the predecessor and path length values of all vertices will have been set. Now if path length of any vertex is infinity, it means that the vertex is not reachable from source vertex. So in that case, we print this message. Otherwise, we print the shortest path from source vertex to vertex V using this method find path. So now let's see this method find path. This array path is used to store the path from source vertex S to destination vertex V. This variable SD will store the shortest distance from S to V, and this variable count will store the number of vertices in that shortest path. Here we are creating the path by following the predecessors till we reach the source vertex. And here we are displaying the shortest path and shortest distance. Now this is the method main where we have created the graph that we have seen in the example. We have called this method find paths with source vertex 0. Now let's run this program. So the source vertex is 0 and the shortest path and shortest distance from vertex 0 to all other vertices of the graph are displayed in this output.